Good afternoon. Can one of you confirm you can hear me and you can see my screen? Can you hear me?
Yes, sir.
Okay, great. So welcome back and thank you for joining this class on a Saturday and rescheduling according to the convenience. I'll share my screen and we start. Are you able to see the full screen like this, or I have to reshare? Can you see my slides in the full screen?
Yeah, yes, sir.
Okay, so it should work. So we'll continue to discuss how to formulate our intelligent agents solving search problems. So how to formulate our search problems. And the issue that we discussed today will be the abstraction issue, how to make our problems abstract so that number one, the problem can be solved in realistic time. And another, that we can generalize our intelligent agent problems so that many different problems can be solved by this. So the issue of abstraction will be for just recapitulating what we have done so far, that problem solving approach of a rational agent requires the statement of six aspects: state space, initial state, action state space, what are the actions possible, transition model, action cost that we discussed yesterday, and the goal state, or there may be multiple goal states, and which may be then described in how to calculate our score, either or maybe provide some score so that a single score performance measure can be defined. So now question is, when we define our real problem, do we have to state it explicitly? Our actions have to be stated explicitly. Like if I'm trying to navigate, should my action state mean going from one place to other where these places are identified, or should be a certain abstraction involved in that? So many a times we have a choice that we may make our abstractions very abstract. So, and they may not include all the details. We may not, if we want to, for example, say that we have to go drive at this speed, this speed, and we have to say right or left, and it may not exactly mean we are going 90 degree or we are going 78 degree or 88 degrees. So some kind of an abstraction where we are leaving out details are important to solve the problems in a realistic manner. On the other hand, if we leave out details too much, and if we just say we are turning right or left, or if we are solving the problem in a very abstract manner, then some details which are important for solving the problem may be lost. So a balance in the abstraction that we assign to our problem is very important. And then these considerations we look at today. So this is an example here. So again, level of abstraction required by an intelligent agent. It depends on the kind of problems we are dealing with. Precise level of abstraction depends on the nature of problem. But these are the two considerations we have to look at. First is the question of validity, and the second is the question of practicality or convenience. So when we say validity of the defined problem, means if we leave out the details which are important for solving our problem or reaching the goal, then it is not good. We have to have all the details which are required for reaching the goal. But if we put too many details into our model, then our model may become too complicated or too cumbersome, and maybe difficult to solve, or sometimes maybe even become invalid. So here I've taken a quick example. I'll come to this example later on again for another context, but let us say this is I have a moving tile problem, and made up of 3 by 3 tiles, which are numbered in the columns 1, 2, 3 as a matrix, and in the row 1, 2, 3. And I have an empty block here, which is shown in black. And let us say this is a very simple problem. I want to move A, B, C, D, A, B.
Have you transitioned to another slide?
Yes, we have to have a transition of one cell to another cell. so that all these.
So we can't see. We are just on. We can't see your slide that you're presenting.
That's what I was asking in the beginning. So I think that is what happens. I'll reshare the slide. Sorry. Just a moment. So somehow in Zoom, I've been trying this and it works in 2 steps for me. So can you, so that means you may have not read my this. Can you now see this matrix?
Yeah, now we can.
Okay, great. Thank you for pointing out. So, I was reading from this slide that there are two aspects, validity and convenience. Now you can read that from this slide, but I was not describing this matrix. So let us say I have this tile problem, and I have a toy or a game which is made up of these 9 tiles, 3 by 3 matrix. And the columns of the matrix are represented by 1, 2, 3, and rows also represented by 1, 2, 3, as is shown in this table in red color. Now, let us say the goal state for me is when these letters A, B, C, D, E, F are arranged in a perfect order. Let us say that is my goal state. And now action model is that I have to move these A, B, C, D, and then these A, B, C, D can be moved to only to the blank tile or empty tile. So for example, I can move A to this black, and the black will be exchanged. The blank will be exchanged to A position, or it may be exchanged to B position, etc. So the goal can be defined as how many action cost may be defined. One move means one cost, unit cost model. And then at one time, action can be going from position number A goes from position 1, 1 to position 1, 2. Or another action could be that B goes from position 1, 3 to position 1, 2. So this is a kind of detailed description of my action states and the real states, where and the environmental state environment can be described as, or the current state can be defined at A at position 1, 1, B at position 1, 3, D at position 2, 1, F at position 2, 2, etc., etc. So this may be a complete description of my current state, and the action states may be going from position 1, 1 to 1, 2, going from position 1, 3 to 1, 2, etc., all exhaustive combinations. So this is a detailed description. Can you think of a simpler description or a more abstract description of action space? Do you understand the way I have described this action state space? Action space is just every position I define, and I define what letter I'm talking about, and I say it goes from this position 1 to position 2, and their position 1 and 2 are identified 1, 1, 1, 2, 1, 3, etc. So you will see that in my action space is made up of a very large number of actions. So can you think of an abstraction of this? Just whatever comes to your mind, tell me if I can describe this in a simpler term so that the number of actions I have to define becomes smaller. I give you a little time to think about it. Yeah. Aditya, you're saying something.
Yeah. Given any letter, it could be either horizontally exchanged with the blank one or vertically exchanged.
So you can say turn right or turn left. So
Yeah.
now if you define it this way, turn right, left, up and down. So this can be, the moves can be defined right, left, up, down. And also you have to define which letter you are moving. Is that right?
Yes.
So how many such actions will be possible in this case?
No, if you define right, say suppose right, we don't have to mention the letter because right would only mean this unique at the B.
Now, which one are you moving? You are moving letter or you are moving the box?
We are moving the blank tile.
Yeah, so this is interesting thing. So mostly the blank tile problems, we don't define in terms of the occupied tiles, we define in terms of the blank tile. So we can imagine this to be actually a blank tile moving. And wherever the blank tile moves, it exchanges the letter with that particular position. So now you have to just define, because now if you're focusing on the blank tile, so you need to just define one action, that is right, left, up and down, 4 actions. So our action space is now made up of only 4 elements or 4 possibilities. Is that right?
Yes.
So in this way, I can define it completely. If diagonal moves are also allowed, then it will become how many?
8.
8. Yeah. So for diagonal positions, if it depends on how we are defining our moving tile problem, if diagonals are allowed, it will be 8. If diagonals are not allowed, it will become 4. All right. So it doesn't matter whether in the at position 1, 1, up position is not allowed. So in some cases, some actions will not be valid. That is another thing. So the point is that if you describe in complete detail position wise, this is too many actions and this is too many details, which we do not require. So converting our problem into abstractions is important. And if we give too many details, it will become impractical and unnecessary also in some cases. But at the same time, it should not become so abstract that the actual problem that we are trying to solve is lost. So I'll take some examples from there in that. Okay, so you basically understand what we mean by abstraction. That is, we define our problem in such a way that we can describe a kind of a general formula that will describe our action model, transition model or action state space that I go from state 1 to state 2. These are the action states possible. So otherwise, yeah, I could have made a more detailed description that I just had started with. So now, this is another example. If suppose I want to write my path from I want to go from JNU administration to Delhi University South Campus Library. So sometimes I might be tempted to write abstractions like admin to library. So is it a correct abstraction? That is, I'm not saying JNU administration or DU South Campus Library. I just say admin to library. This is a kind of an abstraction I have introduced. So is this a valid abstraction?
No, not defined properly.
No, it is defined, but it is not valid because this generally.
No, but how would you know what is admin?
No. Let us say we know the administrative blocks in a university. We know the library. What is library? But this does not apply to us. Our case. Let us say I know about all the universities, the admin and library. But the actions which go from admin to library, they are not generalizable. Or any path that goes from one admin in one university to another admin in another university, they are not equivalent. If a generalization does not exist between different administrations, just because of they are doing a particular function, you cannot generalize them for the context of root finding. But if I am doing something which is relevant and which can be generalized across the administrative buildings in the universities, I can use that abstraction. You understand the difference I'm trying to make here? When I can use administration as an abstraction, when I cannot use it as an abstraction. Can all of you understand this? That in some cases, when the generalization is possible, then I can, generalization is possible means all different instances of similar problems where this terminology would apply should be solved in the same way. Then I can utilize that generalization, and the goal states and the initial states, these abstractions can be utilized. But in this case of root finding, it is not possible because the path from one university's administration or another university administration, there has no correspondence. Even though they may have similar names, they may be doing the same thing. So this is a requirement of the generalization to perform. Then should I have to be specific, like in the last example, I said A block A, B, C, D, etc. Do I have to say JNU admin? Then I say road, and then I say library. So this is I go from the JNU administration, take the road, and go to the Delhi University Library. In these three notations, which one is an invalid abstraction? In this, JNU admin is a state, and Delhi University also is a state, environmental state. Road is the action. So this road is actually invalid because road is too general here. I have to specify what road I'm taking or turning right or left. So this is again invalid abstraction of the action state. So either my states may be invalid, as in this first bullet point, or my actions may be invalid. In both cases, these generalizations do not apply.
Would there also be the case that road is invalid because there might not exist a road in some cases?
Well, if I know that my first stated admin and second state is DU library, and let us say an action exists between them, that this action should be properly definable. So if in one place I say road, in another place I say road again, it should mean the same thing. That is the requirement. But in this case, it does not mean the same thing because multiple roads may exist, and in one case road may be shorter, it may be allowed, it may not be allowed. In 3 directions may be possible in some places, 4 directions may be possible in other places. So road, even if it exists, unless it is generalizable, we cannot use the abstractions. All right. So going further, this is the other example. First, I gave you the example that there may be invalid abstractions. These abstractions I cannot perform. I have to give more detail. Which road, whether right to the red or left of the road. And I cannot say start driving. Now this gives another example in this slide. You will see that impractical abstractions. You say car start, D-clutch, turn 20° right. These are different actions we can take. Speed 40 km/h. So these are the kind of abstractions which may be valid or which may be insufficient. What do you think about this? Let us say one by one. If let us say I'm saying car start, is it what kind of abstraction is this? It is impractical or it is insufficient? I mean, if I describe my car driving from one location to the other in such details that I tell car start for first action, D-clutch second action, turn 20° right is third action, speed 40 km/h, my next action, and so on. If I give these many details, do you think these are too many details or these are too invalid generalizations?
I think these are too many.
Yeah, too many. These are not required. These are insufficient. Now the question is, which details should I consider to be too many? Too many. So there is a rule now that this rule should be followed. Then we can say that my details are enough or my details are too many. And this rule is like this, that if you have an abstract state A and you have an abstract state B, this is the level of abstraction that you want. Now, within the abstract state A, there may be extra details. So with those extra details, these states A become substate of A. So state A may be composed of substate 1, substate 2, substate 3, and maybe more. Same way, abstract state B may be composed of 3 states or 4 states, and abstract state C, etc. Now, the rule is that if there is a path from every actual state, the substate, because actual state is actually completely detailed state, but we are not using actual state, we are using abstract state. So if there is a path from every actual state of the abstract state A to every actual substate of the abstract state B, then there is no need to define substates. So that means there should be a path from every substate to reach there. And if that action that we are writing between these two states is not impacted by the description of the substates, then I do not have to give those details. So this is called sufficient abstraction model, where you have achieved the sufficient abstraction without giving too many details, but also valid abstraction, which is required for describing my actions taken to be taken to reach my goal state. Okay. So this is another example. I mean, this is just for those of you who are interested in connecting this knowledge with the literature. And so you might think of the Sherlock Holmes had a lot of details. And the question to him was that if you are given a spy is given thousands of pages of a document to reach a conclusion, then it will be too much of work for an intelligent person to go through those details. So an intelligent person does not always work with every minute details that he has. So in some cases, it is completely impractical to look at all the details that are available to you. So a complete abstraction, when we do our intelligent tasks in our daily life, we do abstractions and we kind of generalize and we drop out the details which are not important for the task we want to perform. So the right level of perfect abstractions, Sherlock Holmes is considered to be the benchmark of intelligence by many. And in this, he describes why leaving out the details is very important, and leaving out the details which can be actually left out. Okay, coming back. So another problem solving approach in the task environment, another way of looking at it is the difference between the standardized problem and real world problem. So a standardized problem is it is a kind of an abstraction of problems, that many different types of problems can be solved in the same way. For example, we defined just now the tile problem, moving tile problem. Moving tile problem is a kind of an abstraction of many problems. In many real life problems can be thought of like a moving tile problem. So many times when we define an intelligent agent, so we may be first defining and trying to find methods of solving the standardized problems. And in another scenario, we will pick up one of these standardized solution and apply to the real world problems. So as it has been shown in this slide, that a standardized problem illustrates or exercise various problem solving methods. It will become more clear to you as we take actual cases. It has a concise, exact, the descriptions are exact. It is suitable as a benchmark for researchers. So for example, if we define a problem of the moving tile, I will find out somebody will do theoretical methods and find what is the fastest method to solve a moving tile problem. But in reality, you are not moving tiles in real life. But many of your problems may be converted into moving tile problem. So then the problems that you are able to convert to the moving tile problem, so you do not have to solve that problem in every time in this, do not have to find novel solutions for your problem. As soon as you say that my problem can be defined as a moving tile problem, you can utilize all the solutions that people have provided for the moving tile problem. So when you will encounter a real world problem, you will have to look for that my problem maps well with one of these problems, standard problems that we have solved. Moving tile, it may be a moving tile problem, it may be a jigsaw puzzle, it may be many different types of problems. Some of them I will cover. So as stated here in 3 bullet points about the real world problem, it is a problem whose solution people actually use. It has a idiosyncratic, but it is idiosyncratic. It is not standardized from formulation. You do not say navigation problem going from JNU administration to Delhi University Library. It is not a standardized problem. It is a real world problem. Now, a standardized problem will be given a graph, given the locations of all the possible nodes. If I have to reach a destination in the fastest manner through the graph, what is the fastest way of finding a way from one node to the other node? This is a standardized problem. So, but if I have to actually navigate to the real problem, the JNU administration to Delhi University or one place to the other, many different types of navigation problems can be solved by the same standardized problem. So, and it is not just about route finding, it may be some other totally different problem, solving say, if I have different protein sequences. So many of the biological problems which may not have anything to do with a real route or real navigation problem may be formulated as navigation problem and solved. So some of those examples we will take. So all you need for the real world problem is that a sensory model and the transition model. In the standardized problem, you do not have to explicitly say what is your sensory model and what is transition model. In the real world problem, your sensory model and transition model may be different. In each of the real world problem, these models will be different. costs may be different. And your standardized problem may use just cost as an abstraction and try to solve different types of problems using those methods. So this is another case. This is called the grid world problem. So this is a standardized problem again. So let us say an agent that can move between states which are identified by grids and only predefined moves, adjacent, horizontal, vertical, or diagonals. This is the moving tile problem that I just showed. This is another variant of that, where I do not have just a moving tile, but any tile which is annotated by A1 to D4, they can move around and can take additional actions such as hitting something in. So it may be 2 players or 1 player. That is another thing. So what are the different moves that are possible? So this type of problems, many different problems in real life may look like grid world problems. And we'll say some examples how to formulate our problems to be grid world problems. This is now an example of a grid world problem. So this is the standardized grid world problem. Now, I do not show the next slide. I just gave you a glimpse, but can you now think of the 2-tile vacuum cleaner that we have been talking about? That 2-tile vacuum cleaner can be treated as a grid world problem. If it were to be treated as a grid world problem, how will it look like? You remember how the problem of 2-tile vacuum cleaner was defined? That vacuum cleaner is moving around on 2 tiles, A and B, and the state of the state space can be defined as whether each tile is clean or dirty, and sensory model will give this information to the vacuum cleaner. Then vacuum cleaner will take a decision to turn right or to turn left, because they are just 2 tiles arranged horizontally. And another action possible for the vacuum cleaner is suck or not suck. So now if you have to define this cleaning problem as a grid world problem, what kind of grids will you form?
There would be 2 grids, let's say A1, A2, and the agent can move only in the horizontal direction, right, AF.
So how many nodes will you require? How many blocks will you require? What kind of matrix will you make?
What matrix? I didn't get.
I mean, for grid world problem, you have to make a grid like this that is shown on the current slide. So where each of these nodes actually is a state. So what states will you define? And how many states are possible? Okay, let's break down the problem into these 3 parts. How many states are possible for the vacuum cleaner world?
4. It could either be in the left or right, or it could either be the left could be dirty or not, or right could be dirty or not.
4 are enough? There's one more. Okay, let me show you here. This. So your environmental states are, as you said, clean, dirty. Your vacuum cleaner state, where it is present, left, where it moves, left or right, this kind of action, but to go to right or left. And then environmental state also left or right. So basically 2 into 2 into 8. 8 states are possible. And how it moves from one state to the other is these are the possible actions. So this is, you can present this as a matrix, but for quick.
Can you explain again the 8 states? I didn't get it.
Yeah, I'm explaining this. So on this representation that you have here, so you have, say, if you can see my mouse, this is the first state. So this state is where the this state is defined. This vacuum cleaner goes from the left and remains on the left, or it it is current in the, it is dirty. This tile is dirty. This tile is dirty here. So this is the complete description of the state. And from this state, it can go to this state by a single action by going to the right. When it goes to the right, it can go here. Rest of these other environmental conditions are not changing. So two states, like here I have written in 3 lines. First state is the vacuum cleaner state, whether it is in the left or in the right. Second state is the environmental state, whether it is clean or dirty.
But sir, the side in which it is not present, how would it know if it is clean or dirty? It has no access, right?
Yeah, it does. It may have access or may not have access. That is not important here. But the complete state can be defined only in this way.
Okay, then I got it.
Yeah, it may or may not know. That is immaterial. But the entire state is changing. Okay. Yeah, that's a good question. So all the states may not be known. So it is a partially observed from the vacuum cleaner point of view. It may not be completely observed. It may be completely observed. That doesn't matter. But the entire space of the, or entire goal, not goal, state space can have 8 values. And these 8 values are represented by each of these conditions. Each pair of tiles here is one state here. And then these arrows here are showing the actions which will take them from this state to this state. For example, this arrow will take, by sucking the dust from this state will be converted to this state. If I have to number them 1, 2, 3, 4, 5, 6, 7, 8 in the horizontal manner, then from state 1, it can go to state 2. And from state 1, it can also go to state 3. What action will be required from going from state A to state 2 is it takes this arrow R. If it turns to right, it will reach state 2. If in the state 2, if it turns left, it will return to state 1. And if in this state, if it does sucking, so by this action S, it can reach from state 1 to state 3. And this is how all the formulations from how the vacuum cleaner can go from, or how the action can take your state of the entire rational agent from one state to the other. All these combinations are shown. So in this way, it can be treated like a grid world problem. So where you have basically eight grids. And the initial state, any of these states can be the initial state, which is the current state. And 3 possible actions, we have already discussed them: 2 right, 2 left, and suck. In 2 dimension, 2 more actions will be added. One can define a diagonal action also if that diagonal movement is possible. So this is a one-dimensional based problem basically, where you are able to have 8 states. But if I had 3 tiles, if I had 4 tiles, or if I had 2-dimensional floor to clean, then of course more actions will be added. And the transition model is how the action changes the position. If the tile turns left, where does it go? So if it turns left, it remains here because there is no more tile there. If it turns right, where does it go? It goes here. So that is why this particular transition model adds 2 more states. And the goal state is that the floor should be cleaned. In this case, this particular state can be considered to be a goal state. And if my current state is here, how many actions are required to go from state number 1 to state number 8, and where state number 8 is my goal state. So my formulation now can be thought of like I'm in a grid, and in this grid, I have to go from one grid to the other in this matrix, and then so that I can reach my goal state. And of course, the action cost. In this case, moving and sucking are treated as equal cost, but you may have another model where the action cost of moving from right to left is different than sucking. This is another example. This is a puzzle called Sokoban puzzle. I don't know any of you know this. So this Sokoban puzzle works in this way that there is a player who has to move these boxes to the empty blocks. And this is this Sokoban puzzle you can also find, and this program is actually available, code. You can implement it yourself. So for a world with one agent, so that is one player, And his goal is that there are some obstacle blocks, and some are empty blocks. So it has to, there will be some boxes. Let us say there are B boxes, and there are N empty blocks, empty positions. So one by one, this player has to move that box from one position to the other, so that all the boxes can be reached in a particular order. So for a world with one agent player, you have N non-obstacle cells and B boxes. So again, by a simple combination, how many states are possible? N into N factor NCB, which is N star into N factorial divided by B factorial and B factorial states. So in this puzzle, where the boxes are being moved, B boxes are being moved on N non-obstacle cells, the number of combinations which describe completely every cell. So the number of states that can be defined for this game or this puzzle is actually quite large. So just even if it is an 8 by 8 grid, then you will have 200 trillion states. These numbers are huge. So that is why you cannot solve these puzzles exhaustively. You need to have some intelligent methods to reach the goal state. Initial state can be anything. And action will be move a box, right, left, up, down. Goal state is move all boxes to the designated place. Let us say the designated place is here or anywhere which is fixed. And box's new position is a transition model, and the action cost is 1. So this is another example. This can be thought of. Each of these states you can define 8 by 8 boxes like a grid problem. And then your goal is to reach from the one grid location to the other grid location by a particular model. So this problem of sliding tile I already took, so I'm not repeating it. Okay, anyway, it is there. So if this is my moving tile problem that I showed by a black tile earlier, and where blank tile is being moved. So not repeating it. So now we'll come to how we actually solve the standard formulation of the 8 puzzle. So a state description specifies the location of each of the tiles. Initial state is defined. Actions, I think I already described it. I'm not repeating. Yeah, okay, this is another problem. And this is a very interesting problem because it is a grid problem, but it looks like an infinite grid problem. That is, the grids in which I am taking actions are not finite. And this is a Knuth conjecture. And in the Knuth conjecture he gave a theorem. It said that if you start with number 4, and you can put any number of factorials, any square roots, and you fix any number that I want to combine, get number 5 out of this, or number 6, any number that you want can be generated by using a combination of operations of factorials and square roots. So it says Knuth conjecture that starting from the number 4, a sequence of these 3 operations, which is square root, floor, and factorial operations, a combination of these 3 operations can reach to any desired number. I want number 10 from this. So, and this number 10 can be reached. Now, this is a hypothesis. This is the kind of assumption that solution exists. Now, this will become a grid problem for me, that how do I reach number? What is the fastest way of combining the factorials and the square roots so that the desired number can be reached? So this can be solved also as a grid problem. And it is an infinite grid problem. The grids will be generated in real time. Yeah, I put two square roots, maybe one factorial, and then 2 factorials, etc. In what order I'm putting it, what actions are possible, I can keep on expanding until I get the number. So these infinite problems can be solved until how this infinite problem is being solved here is that I find some method of generating my path from the current state to the next state. And I keep on trying using some systematic principle of formulation. And then as soon as I reach the goal state, as soon as my new number is the desired number, I stop. So I do not have to scan the infinite space to reach my answer. So this may take a very long time or may take a short time. So the goal of a good algorithm, good rational agent will be one which can reach this answer in a reasonably fast manner. Okay, so again, formulation of this will be that you have states are positive real numbers. Initial state is fixed by the Knuth conjecture, which is 4. Actions are 3 types of actions are possible. Apply square root, floor the number that you have, factorial operation, and factorial operation works on only integers. That is why this floor is required. My transition model is that as given by the mathematical definition of the operations, that is this is my transition model. If I have the factorial orders and the square roots, this is my transition model. Then the goal state is also the desired. I want the number 100, I want 200, whatever is the desired positive integer action cost. So this people have written codes and different methods to solve this kind of a grid problem. And sometimes these factorials will take us to a very, very long numbers. So that is why this is a computationally and algorithmically challenging problem to find the best solution for how to find the best combination of these 3 operations that are action operations, which can lead to a number that I desire. Okay, I think I stop here for today. I can take your questions.
In this Knuth's conjecture, the action cost would be something like how far it is going from the desired number.
No, in the action cost will be typically defined by a single action. So it doesn't matter how large is the number. That doesn't matter. So action cost is how many operations are required. So 3 operations or 3 actions are possible. One is the factorial, one is the square root, and one is the floor. So how many operations are required? So you will have to have a sequence of operations which will take you from your current number to the desired number. So now in what order to generate these operations, that is the challenge. And that is where your algorithm of solving this grid problem will apply.
So adding an extra operation increases our cost.
Yes, because computationally it means one floating point operation, floating operations. So that can be equated to, or you can think of this as a computational complexity of the problem in solving it. From the beginning, we do not know how many operations are required to reach, even as I showed that even from reaching from number 4 to 5, a large number of operations may be required. So that is where the algorithms will play a role. That should we keep on adding the factorials first, or should we keep on adding the square roots first? Should we go to the smaller number? So that is where the methods for solving these grid problems will apply, and that is what we will discuss. So in some sense, what we are trying to do here is that this is a real problem. Knuth conjecture is a real problem, real world problem. And grid problem is an abstraction, or it is a standardized problem. Now, if I have a method to solve the standardized grid problem, Knuth conjecture can be solved as a grid problem. So I do not have to specifically look at Knuth problem. I simply convert my problem, my Knuth problem, Knuth conjecture, into a standardized grid problem. And now the methods that are available to me to solve the grid problem, I will apply them. And this problem will also be solved. In the same way, the Sokoban puzzle can be solved. The moving tile problem can be solved. All of them, first step will be to convert these real world problems into a grid problem. I define what are my grids. I define what are my actions on the grids possible. And I define what is my transition model and what is my action model, and then a cost model. Once I have defined them, all the problems will be solved in the same way. That is the power here.
When defining the grid problems, we assume that we have it is not partially observed, that we know everything about them.
No, it may be partially observed. The entire grid may not be visible to me directly. I may be within the grid, I may be currently located on one particular location. Only the environment around me should be visible to me. I do not have to be aware of what will happen 100 steps ahead. So I can dynamically generate my grids. Like in this Knuth problem, I'm starting with 1 factorial. So I should also only have a way to generate 1 square at one time. If I am adding 1 square root, I have a way to do 1 square root. I have a way to do 1 factorial, 2 factorial, 3 factorial. I can keep on adding. So in an iterative manner, in a recursive manner, I can keep on generating my grid. So some recursive formula, some recursive way of adding new grids should be available to me, where these actions, where these models of transition model and sensory model are available to me. Okay. Fine then. You can do this exercise. You can look for these three or four problems that I have mentioned today. The Sokoban, moving tile problems. You may find these codes and try to implement yourself and see whether you are able to implement these. A lot of these codes are available in public domain. So you can try to implement and just enjoy this. Okay. Thank you then. We'll meet again in the next class.